Let's expand a little bit on your book's definition of Newton's first law. So this is the definition given in your book, that for an observer in an inertial reference frame, with no other objects exerting forces on the system, or when the forces exerted on the system add to zero, the system continues moving at a constant velocity. So first, let's just look at what this means at face value. So that means, let's say we have some particle here, and it's initially moving at some velocity v. We look at it some later time, right? It's moved, and it's still moving with the same velocity v. And note that I say velocity, not speed, right? So the direction matters too. So it's neither its direction nor the magnitude of its speed have changed. But then again, this also means the same thing if it was initially at rest, right? So if we have like a rock sitting on the ground, this just says, since its velocity is zero, it's going to remain zero. For most textbooks, that's about the entire description they give of Newton's first law. But let's expand on it a little bit. So this is some material that's going to come later in the book. And so far, I've really only found one undergraduate textbook that kind of covers this in what I think is the right way. But unfortunately, that's a calculus-based book, and so it doesn't really apply to this class. But what Newton's first law is really telling us is about something called momentum. And we're going to visit momentum in a few chapters. But it's worth introducing right now because this is exactly what Newton's law is saying. This is going to be one of those times where the standard conventions of physics doesn't really make sense, because for momentum, we typically use the variable p. I think it had to do with the fact that they used to call this impetus before Newton's time, but for whatever reason, momentum is we typically denote as p. We say that the momentum is the mass times the velocity. And what Newton's first law says, if there are no forces on an object, then that means the momentum is constant. So this is basically the same thing as Newton's first law. But again, what we're going to see later is what it actually takes to change the momentum, to change an object, right? And Newton defined that as a force. And really, we can say that's the definition of a force. A force is something that changes an object's momentum. And so mass can actually be thought of as how much an object resists having its momentum changed. So for example, this is why it takes a larger force and it's harder to change the direction or the motion of a train as opposed to a hamster. And so what Newton's first law is really saying is that if you're out in space and there's no other particles, there's no stars, there's nothing else around you, you're going to keep moving in the same direction you're moving forever. So anytime you see something slow down or speed up, then that tells you that there had to be some force that was acting on that to slow it down or speed it up. Because as Newton's law tells us, his first law tells us, if there weren't any other forces acting on it, then its velocity would remain constant. Now, the one other caveat is also that it says that we could have a system where all of the forces add to zero. And so that means, if you're pushing on an object, so for example, if we have, a refrigerator and you're on one side of it pushing it and someone else is on the other side of pushing it, of course, that's going to have the same effect, right? So even if the refrigerator had been moving initially, if you and your friend were both pushing on it with the same force, then the refrigerator would keep moving at the same constant velocity. And that's all Newton's first law is really telling us.